Okay, I'd like to resume where we left off. We're talking about bits, bytes, and words and ways of representing them. And we discussed how you can use the hexadecimal numbers, which are 4-bit numbers, to simplify binary numbers. And we showed how those 4 bits can be represented by the numbers 0 through F, or 0 through 15 in decimal. And we talked about how you convert them by using powers of 16 or places. So it's sort of like when we talk about decimal, we have powers of 10. Well, in hexadecimal we have powers of 16. And we talked a little bit about ASCII and how the ASCII codes are represented on a chart. And now I'd like to talk a little bit more about bits, bytes, and words. A bit is a single on or off value, and it's possible for the CPU in your computer to retrieve a single bit, but it actually has to do it by getting a byte. A byte is the smallest piece that the CPU can actually get from the RAM or from a hard drive or something like that. So byte is actually a standard piece of information, and a byte is just big enough to hold one single character, like one of the characters on a keyboard, a letter, a number, punctuation mark. Words are bigger chunks. A word consists of more than one byte put together. So standard size words are 8, 16, 32, 64, 128, 256. Those are some sizes, and others as well. Usually they're multiples of 8. Although there have been some computers that use weird sizes like 12 bits and so forth, but most of them are either 8, 16, 32, or 64-bit chunks, and we call those words. And one of the word sizes, the 8-bit size, has a special name, byte, so we usually refer to that as just a byte. Now, data is often sent out of your computer as bytes, but it has to be sent in one of two possibilities, and that is either serially or parallel. Now, we're talking about data being sent from one device to another. It might be sent, for example, your computer would send information to a printer, or it might send information to an external hard drive or receive information from it. Or it would send information to a digital camera or get information from a digital camera. All of that data has to be transmitted in some way. And there's two ways that that's done. One is called serial, which is 1 bit at a time. And the other is parallel, which is multiple bits at the same time. Now, the very simplest serial, let's talk about serial. The very simplest serial could be just a single wire. In reality, it would be 2 wires because there would have to be probably a ground involved. But they used to have, in fact, in the early days of electronic communications, the first type of electronic communication was the telegraph. And what they'd have is a single wire, and they would have a battery connected to one end of the wire, and they'd have a switch called a key, and they'd turn on and off that switch to send the code over the wire. And so that was kind of a type of serial communication. They call it the telegraph. And computers still use that kind of communicating. They can use a single wire. So that's the simplest kind of wiring you can have. It saves on the wiring. The disadvantage is it only sends 1 bit at a time, so it tends to be slow. Although some serial transfer can be very fast. For example, we have what they call USB, Universal Serial Bus. That's actually a very fast type of serial connection, fast enough to keep up with most devices. So serial doesn't necessarily have to be slow. Parallel, on the other hand, does transmit data more than 1 bit at a time, so it has more wires. Now, how would you actually send data over these wires? Well, if you're talking about serially, what you would do is you would be representing that as either a voltage on the wire or maybe an electric current flowing through the wire, and you turn that on or off, and you do it. And so, like, let's say we're sending the letter the word the here, THE. Well, the binary code for the letter T it's an ASCII code, is this number here, and that's, you see, represented as ons and offs. So here we have 0, 1, 0, 1, 0, 1, 0, 0. So it's represented as ons and offs on the wire. And then they have the letter H here. We have that as 01101001000. Again, wherever you see the 1, you turn the wire on. Wherever you see a 0, you turn it off. And then we have the letter E here, 01100. See where the zeros are, we have it off, then 1, and then 0, 1. So the wire goes on and off. Now there's also timing involved. There has to be, some sort of synchronization going on here so the computer knows when to expect each particular bit. So they'll actually often have an extra bit called a start bit, which would be between each one of these bytes here to help to keep things synchronized. Or they might have an extra wire called a sync wire to do that. Parallel data is where you have more than one wire. So we might have, instead of just having one wire carrying the bits, we could have maybe 8 wires, like a parallel printer port has. It has 8 wires. So that means it can send a whole byte at once, and so it's a lot faster, or it tends to be. So we could send, let's say we're sending the message to the cat here. Well, then we have the letter the letter T here, which is 0101010, and that's all on the same at the same time on different wires. So each one of the wires carries one of those bits. And then when we send the next letter, we have again each of the bits for that letter on a separate wire, and so it can send that much quicker. Parallel data then can be transferred in groups of 8 or 16 or 32 or 64 bits, depending on how many wires we have. We have to have enough wires to handle that many bits. So computers then computer data is usually sent then as zeros and ones, either over a single wire at a time or over multiple wires at the time. Now we'll talk more about serial data transfer later in the class as we talk about some of the devices that use these types of data transfers. And we'll find out that actually serial data is often transmitted not with just one single wire for each bit. Sometimes they use 2 wires. That's called differential signaling, and it really works the same way, except that instead of both wires having the same voltage, they have different voltages, and one voltage goes high while the other one goes low, and then they switch places to represent the 0 and 1. That's actually more reliable and picks up less noise. The old-fashioned serial port used 1 wire for each bit, and the USB actually uses 2 wires to represent it, but it's still considered serial because we're really only sending 1 bit at a time, even though there's 2 wires involved. Computer numerical values. Metric prefixes are often used with computers, and we use them. You've probably heard these a lot and think too much about them. But we use metric all the time in other things as well, and it's the same prefixes used in computers. Now, we can talk about, for example, the bits of memory or of a number. Or we could talk about the number of bits or bytes in a memory, or we could talk about speed. All of these things could use these metric prefixes. Now 1 bit, or a bit per second being sent, is one way of measuring the speed at which data is transferred. We call that bits per second. So you could easily talk about how many bits per second is sent over a modem, for example, over a telephone. The fastest modems that they make for regular telephones is about 56,000 bits per second. Sounds pretty fast, but actually it's pretty darn slow by other standards. But it's what a lot of people talk to the internet or communicate with their internet service provider with a modem, and it uses serial in bits per second. Bytes per second means that we talk about, instead of talking about individual bits that are sent over, we talk about whole bytes, and that would be 8-bit chunks. And that would really be equivalent to characters per second. How many characters do we actually send? So these are speeds here. Now, a lot of times when we talk about bytes in bigger amounts, like megabytes, a megabyte would be 1,000,000 bytes. Or we might talk about kilobytes, that would be 1,000 bytes approximately. So maybe we'd say 256 megabytes, that would be 256 million bytes. Or 4 gigabytes, that means billion bytes, right? 4 giga. Those are called metric prefixes, and here we see some of those metric prefixes. Here's mega and giga. Mega means 1,000,000 and giga means 1 billion. A mega is 1 1 with 6 zeros after it, or 10 to the 6th power. Giga is 1 with 9 zeros after it, or 10 to the 9th power. And then you can go beyond that. Tera, some hard drives are terabyte drives. It means they have 1 trillion bytes, or 1 to the 12th power, 1 with 12 zeros after it. You can also have really small numbers. You can go down to kilo, that's 1,000, but you can have milli, which is less than 1. Right? Some of these numbers represent small numbers, so milli is 1,000th, or 0.001 of something, or 10 to the minus 3, or million is 10 to the minus 6, or 0.00001. That's a millionth of something, or nano is a billionth, or 10 to the 9th, and pico is a trillionth, or 10 to the minus 12. All of these units are often used with computers in one way or another. Maybe you'll talk about how fast a memory is. It would be measured in nanoseconds, for example. Or how fast access is on a hard drive. That would be measured in microseconds. So there's lots of different ways we use these metric prefixes. Now, when we talk about, with regard to some things, though, those metric prefixes have a slightly different meaning, although it's not that big of a deal. A kilobyte actually represents, when we're talking about kilobytes, it isn't really just 1,000, it's actually base 2 1,000, which is actually 1,024. Alright, it's the base 2 number that's closest to 1,000. And a megabyte really isn't a million, it's actually 1,048,576. And a gigabyte, well, that's not really a billion, it's a little bit more, and a terabyte is a little bit more than a trillion, and so forth. So all of these numbers are slightly bigger than what they would normally be in the regular metric system, because they're based on powers of 2, but pretty close. Can you name 3 ways in which data can be expressed? Well, they can be expressed as voltage levels. We can express values or data as number systems, such as binary and hexadecimal, or we could represent them as ASCII code. Those are 3 ways, and there's others as well. What is the nominal value of 1 megabyte? Okay, well, 1 megabyte means, what we mean by nominal is what's it close to, or what's it approximately equal to, and that's about 1 million. So if you think of it as 1 million, that's pretty close. So actually it's a little more than that. And so the value of 1 megabyte based on the binary system is actually more than that. It ends up being 2 to the 20th power, which is 2 times 2 times 2, 20 times, which is a little over a million, 1,048,576. Now, we'll come back in a few minutes and talk about the toolkit that we're going to use in our class, but let's take a break.